Okay, guys, we're still talking about law of conservation of mass, and what we're going to do is just read over this article together. I have put this on Google Classroom for you as well. And then at the end of reading this, we're going to talk about what your assignment is for today. So, have you ever lost a screw? The following situation happens all too often. You have taken apart a piece of equipment to clean it up. When you put the equipment back together, somehow you have an extra screw or two. Or you find out that a screw is missing that was part of the original equipment. In either case, you know something's wrong. You expect to end up with the same amount of material that you started with, not with more or less than what you originally had. By the late 1700s, chemists accepted the definition of an element as a substance that cannot be broken down into a simpler substance by ordinary chemical means. It was also clear that elements combine with one another to form more complex substances called compounds. The chemical and physical properties of these compounds are different than the properties of the elements from which they were formed. Okay, remember we talked about that. How, like, for example, sodium is an alkali metal and it's an extremely dangerous soft metal that can catch on fire even when it's placed in water. Chlorine is a poisonous toxic gas, but when they chemically react, they form salt that you can eat. So the properties of the reactants of what you put in are very different from the properties of what comes out. Okay? So in the 1790s, a greater emphasis began to be placed on the quantitative analysis of chemical reactions, and that means the quantity or the amount. Accurate and reproducible measurements of the masses of reacting elements and the compounds they form led to the formulation of several basic laws. One of these is called the law of conservation of mass, which states that during a chemical reaction, the total mass of the products must be equal to the total mass of the reactants. In other words, mass cannot be created or destroyed during a chemical reaction, but is always conserved. And remember, we've talked about this, saying that you could run a chemical reaction on a balance. And if you had a closed system where it was sealed off, your chemical reaction, and you trapped all the products, even if there was a gas being produced, the weight of the products or the mass of the products would be the same as the mass or weight of the reactants. And in addition, we balance chemical equations and make the numbers of atoms going in and coming out equal to show that mass is always conserved during chemical reactions. So as an example, consider the reaction between silver nitrate and sodium chloride. These two compounds will both dissolve in water to form silver chloride and sodium nitrate. The silver chloride does not dissolve in water, so it forms a solid that we can filter off. When we evaporate the water, we can recover the sodium nitrate that was formed. If we react 58 and 5/10 of a gram of sodium chloride with 169 and 9/10 grams of silver nitrate, we start with a total of 228.4 grams of material. So you're adding those two numbers together. After the reaction is complete and the materials are separated, we find that we have formed 143 and 4/10 of gram of silver chloride and 85 grams of sodium nitrate, giving us a total again of 228 and 4/10 of a gram of products. So the total mass of the reactants, the 228.4, equals the total mass of the products, 228.4, a proof of the law of conservation of mass. So now I'm going to press this button and have you guys just quickly watch this video. It's just an illustration of conservation of mass.
States that in a chemical change, matter is neither created nor destroyed. It is only rearranged. For example, let's place 5 zinc and 5 sulfur atoms onto the two sides of a pan balance. The two sides balance because the contents of each pan are identical. Consider the reaction of zinc with sulfur atoms on one side of the balance to form zinc sulfide. 5 zinc atoms will react with 5 sulfur atoms with a tremendous release of energy to form 5 zinc sulfide molecules. The two sides still exactly balance. The total number of zinc and sulfur atoms on each side are still identical, demonstrating the law of conservation of mass.
Okay, and then one more video for us real quickly here. Okay, so summary, the law of conservation of mass states that during a chemical reaction, the total mass of the products must be equal to the total mass of the reactants. Okay, so here's your job today. I posted a flipgrid assignment for you, and I have a little video for you to watch that I recorded that is modeling how I want a response from you. So here's your question. How can we model conservation of mass with either a chemical or a physical change? Record a video of yourself modeling or showing or explaining the conservation of mass in some way. I have included one of my own to show you one possible way you could do this assignment. Here are some suggestions for what you could do. One, you could build a model and use it to explain how you understand the conservation of mass, like I do with the Legos in the video included. You could use dominoes, paper clips, candy, hair ties, whatever you want to use that you have handy in your house to model atoms and molecules. You could, a second suggestion, draw a picture of a model and explain how it shows conservation of mass. And you could use different shapes to represent atoms like circles, triangles, and squares to explain the conservation of mass. Or you could write down a balanced chemical equation and count out the atoms to explain how it shows the conservation of mass. After you're done recording your video, then you would submit it. If you're confused about how to submit your video, I also included for today an explanation of how to do that on Flipgrid. Okay, have a great weekend and good luck.